Hi, Luke McKinney, Prep 101's ENGSCI 1022 instructor. In this video we look at supports and reactions, how to set up the forces and moments that are externally acting on any object to begin many problems.
Supports and reactions. Well, what are they? Well, we know in an engineering statics course, we're going to be doing a lot of equilibrium problems, which means all the moments add up to zero and all the forces add up to zero. And we look at the moments first because that'll help us solve everything a lot faster. We take the moments around the pivot point with the most unknown forces. Well, what forces do we have to deal with? Well, we draw a free body diagram. Let's say we got our bridge over the river, and we add whatever forces we've got acting on it. We've got maybe a wind force of 200 Newton to the right, and the overall weight of 1,000 Newtons down. And if we build that bridge, then immediately it'll blow to the side and it'll fall down, and everyone will be extremely unhappy with you, because we don't just leave bridges sitting there smooth on the ground. We have supports and reactions, and those are the sort of things we have to deal with. Now, how do they work? Well, they're all based on the normal force. We know if we just leave a mass on the ground, it'll feel its weight force acting down, and there's a normal force, sometimes called a contact force. Because it's touching the ground, there'll be a normal force up. It's called normal because it's perpendicular to the surface. So, for example, if you had a ladder leaning against a wall, you'd have a normal force up with the ground, and you'd have a normal force perpendicular to the wall because you're touching the wall there. But we don't just leave bridges and beams lying on walls or against the ground. So what do we have? Well, we formalize the different types of support we have into a couple of different types. The first is a roller, A, and sometimes you see that drawn as a little support on wheels, or maybe it's just on a little rocker like that. But the idea is that the roller, it lets the beam move sideways, so there's no reaction sideways. The support is not reacting to stop the beam moving. If that beam wants to move to the left, the support is fine, go for it. But if this beam tries to move down, the support reacts and pushes against it. So we have a vertical reaction at A. And we see that's just the normal force of one thing pushing against another. But because it's a special situation, we call it a reaction. If we want to stop things moving more, we can use a pin or a hinge at B, and you'll meet pins a lot in this course. Now you can see here, if the beam tries to move right, it can't, there's a reaction against it. If the beam tries to move up or down, there's a reaction against it. And in fact, there could be a reaction in any direction. If we look closer at the beam, we can see what's happening. You got a hole, you got the nut there, so the bolt and the nut. So whatever way this tries to move, the edge of it will react against it. But that's too much hassle to deal with. How can we deal with a vector that could be in any direction? Well, we've already seen that. We just break it up into a horizontal component and a vertical component. So that's how we deal with these. For a pin or a hinge or anything like that, we say there are two components to the reaction. It's got a horizontal reaction and a vertical reaction. And you might be saying, look, how do you know that those reactions are in the positive direction? X positive to the right and Y positive up. Now here's the key, I don't. I have no idea what direction these reactions are actually in, so that's why I assume they're positive. Not just because I'm an optimist, but because I am, but because it makes all the math easier. If I just draw my arrows in the positive direction, then later on, I'll do all my math, and if I find the answer is positive, I'll go, okay, positive, that was in the direction of the arrow. And I know that that positive arrow was to the right. Or if I find out a component was negative, that's negative. So it's opposite to the direction of the arrow. So that's down. And see there, I can read those off directly. Whereas if at the start, if I wasted time guessing which direction they're in, and then I found out they're minus, then I'd have to go all the way back, find out which direction I guessed, and then flipped it. I made a load of extra work for myself for no good reason at all. And, well, if you're building bridges, how popular do you think guessing is as a technique? Not very good. So you see, whenever there's an unknown support reaction, I just assume it's in the positive direction, and then the math will tell me what it is. And that's math's job. You can also get this. The roller we saw at A can actually have a roller on either side, but you still only say there's one reaction. It's just that now it could be positive or negative, but it's still just one nice unknown. Now, if you have a roller at one end and a pin at the other, you'll see this situation a lot on the course. This is called a simply supported beam. And it's a great situation. Why is that? Because I have 1, 2, 3 unknowns, and I have 1, 2, 3 equations, which means I can solve that. I can work it out. I have the same number of unknowns as equations, so now I can find all the support reactions. And in a lot of problems, that'll be your start point of how to get into the rest of the problem. Of course, it's not the only way to support a beam. Another way of supporting a beam is embedding it in a wall like this. So we can see this beam. It's free at the ND, it's not touching anything, so there's no support reactions, but it's embedded in the wall at C. So if you were to look with your X-ray vision, you'd see the beam further in there like that. So what reactions does it have? Well, the beam can't move left or right, so there must be a horizontal reaction at C stopping it from moving. It can't move up or down, so there's a vertical reaction at C stopping it from moving. And it can't rotate, which means there's a moment reaction at C. So there's a moment at C. And remember again, it's very convenient just to assume that these are all in the positive directions. It makes our math handier. And again, we can do the equilibrium equations on this beam to work these out. At D, there's no reaction because it's not touching anything. Now, as we saw before, sometimes you just have support reactions because you're touching something, like our friend the ladder. And I just want to look one bit more at something else we can get there. Here we have a normal force up from the ground. Here we have a normal force perpendicular to the wall. And we have a weight force of this beam falling down. But if we look at this beam's not in equilibrium because we've got a horizontal force out to the left with nothing to cancel it out to 0. So this beam would start to slide and fall down just as we'd expect. And there's a couple of ways to provide one more support reaction to stop that. A simple one is just to have a peg or a block here. And then you'd also have a normal force against the block. Or another way this can be set up is if they just say there's friction with the floor. Well, friction always opposes the intended motion. We know there's a force to the left that'll push this beam left, so there'll be a frictional reaction to the right. And again, now we have a little support reaction we can put on our free body diagram and work things out in the equations. Now, there's a couple more special cases of support reactions I'll want to look at in a minute, but before we do that, we do some examples of what we've already got, because if you're not doing examples of engineering, then you're just not doing engineering. You're just reading some stuff that you'll forget later. So we see here, we have a bent metal beam supported by a pin at A and a roller at B, and we're asked, what are the support reactions? Well, the cool thing is, a huge swathe of this course is all just the same equilibrium problem, where you have a free body diagram, then you do the moment and the force equations. So let's do that. First, we want to get our free body diagram ready, which means adding the support reactions. Now, A is a pin, so it has a vertical reaction and a horizontal reaction. We don't know if they're actually in the positive directions, so we just say they are, and then the math will tell us the actual answer. B is a roller, so there's a single force reaction there. And you notice there's no moment reactions at a pin or a roller, because a pin or a roller will allow things to rotate. The rule for any support reaction is if it prevents moving that way, there's a force reaction that way. If it prevents rotation, there's a moment reaction. So we've done the free body diagram. The second step is the sum of all the moments is 0. Now remember, to take the moments, we need to choose a pivot point. And to make our math easier, we always choose the pivot with the most unknowns. And we can see here, that's A. It's got 2 unknown forces, while B only has 1 unknown force. So we take the sum of the moments around A is 0. So force AX is acting through the pivot, so it produces no moment. Force AY is acting through the pivot, so it produces no moment around the pivot. Then we have 60 newtons, a perpendicular distance of 4 meters away. Now, is that positive or negative? Oh, I should draw my axes to always check. Remember, you're going to be marked on all these diagrams later, so you might as well get into the habit of drawing them right. We can see this force pushing down would be clockwise around A. So that's a negative moment. And then we have force By, and that's a perpendicular distance of 2 plus 2 plus 2 is 6 meters away. That's pushing up. So that would be counterclockwise around A. So that's a positive moment. And so here we have, straight away, one equation, one unknown, minus 240 plus 6 By is 0. By is equal to plus 40 newtons. That's positive, so it's in the direction drawn up at B. That's a little habit to get into. Later on, in trusses and frames, we're going to have multi-component things. So you always want to say where this value is. We've done the moments. Next, we can do the forces. The sum of all the horizontal forces is 0. We have the horizontal reaction at A and nothing else. So that just directly equals 0 newtons. That happens quite a lot. Then, the sum of all the vertical forces is 0. You have plus AY up, minus 60 newtons down, plus 40 newtons up at B is 0. One equation, one unknown. AY is 20 newtons. That's positive, so it's in the direction of the arrow we drew. So that is up. This is a lovely little example of this, and this is also the first chunk of quite a lot of problems where you need to find the external supports before digging into a problem. It's also the method of most of those problems, even once you start doing methods of sections and cutting apart pieces of frames and machines. It's this exact same thing. Let's seize the moment with another example, this one doing an embedded beam at C. And we're asked, what are the reactions at C? And we know our procedure right away. First step is we need a free body diagram before we can do anything. We see at C, it's embedded at the wall. It can't move left or right, so there's a horizontal reaction. It can't move up or down, so there's a vertical reaction. And it can't rotate, so there's a moment reaction. And we assume all of our reactions are in the positive directions. So we draw our little convention to remind ourselves. And a little tip, we should complete this diagram. They've labeled the point C, but there's two other very interesting points here that haven't been labeled. So we just go ahead and label them ourselves. They're our diagram, after all, and that'll be much easier to deal with once we have some reference points. So next, 2. We do the sum of the moments around a point is 0. We always choose the point with the most unknowns. And if we practice, we can see, the point with loads of unknowns. So the sum of all the moments around C is 0. Now, there's already just directly a moment at C. So you add that. That doesn't disappear because it's acting at the pivot. The forces disappear because they're both acting at the pivot. Remember, the moment around a force is the force by the distance from the pivot. And if that distance is 0, then the moment is 0. So the moment due to the horizontal force at C and the vertical force at C is 0. Then we move on. We have a 50 Newton meter moment at D. So we add that, but we see that that is clockwise. So that's minus 50. Remember, in engineering, all the directions are just plus and minus. So even though they've drawn just 50 there in the text, that's negative because counterclockwise is positive. So don't miss that. And then finally, we have a 20 Newton force, a perpendicular distance of 6 meters away. And looking at it, we can see that turns clockwise around C, so it's negative. You see, I call out the full procedure every time I do it, because I'm going to do it 1,000 times in this course, and then it becomes second nature, free and easy. So that equals 0. Lo and behold, we have one equation with one unknown. We find the moment at C is plus 170 Newton meters. That's positive. So it's in the direction I drew, counterclockwise. And then, as always, we move on to the forces. The sum of all the horizontal forces is 0. So the horizontal reaction at C is 0. That happens a lot, but not every single time, so you don't skip it. And even if you do know for a fact it's 0, you still have to say how you know to engineer. And then the sum of all the vertical forces is 0. So we have Cy up minus 20 down is 0. So Cy is 20 newtons. That's positive, so it's in the direction drawn up. Now notice, in all of these, the moment of 50 Newton meters does not apply. It doesn't do anything to the forces. Forces create moments, but moments don't travel back and create forces. So you don't have to jam them in or work them out, anything like that. Now, I mentioned some special cases of reactions, so I want to have a quick look at those now. They turn up later in the course. The slot here, we have a bar AB with a slot and a pin on a bar BC. Now, how does that work? Well, remember our general rules. If an object can't move in a certain direction, there's a force reaction in that direction. If the object can't rotate, then there's a moment reaction. Well, how does that work? Well, in this diagram, first, we would look at the external forces, which sounds like I'm saying something special, but remember, all of our equations, this is always the sum of the external forces and moments acting on something. So what's external to ABC here? Well, A is a pin. So we know we have a horizontal reaction at A, a vertical reaction at A, and C is a pin. So there's a horizontal reaction at C and a vertical reaction at C. See how the more we do it, the faster we get at that. And that is all. That's all the external forces acting on this. You might say, but what about B? B is internal to this diagram, so it doesn't show any new forces on the free body diagram. For example, if I've got me standing here, I know I've got my weight acting down, my normal force with the ground acting up. There's loads more forces acting on me there. There's the force between my diaphragm and my lungs and all of that, but that doesn't turn up on this diagram because that is internal to me. It doesn't show on this diagram. You'd only see this if we cut me apart in the diagram, and now you would see, you'd have the free body diagram of half my weight, the full normal force up with the ground, and then all sorts of internal forces squirting up like that as well. So let's look now at just we want to look at the forces at B, so we need to cut that apart as well. You'll see, you'll do this loads more again later, basically in the frame section of the course. So if we just look at AB, now we have the pin at A and the slot which had the bolt at B. Now A is still a pin, can't move horizontally, can't move vertically. What about B? Well, we remember our rule. If it can move in a certain direction, there isn't a reaction that way. Now that bolt and pin B can move along AB, so there's no reaction. The other half of the rule, if it can't move in a certain way, then there is a force reaction. This pin can't go perpendicular to the slot, so that means there is a normal reaction force perpendicular to the slot. In fact, if you look at it, it's just like the beam was between two rollers, just the other way around, drawing it. How do I know it was up and to the left like that? I don't. I just had to choose a direction, so I chose one, and then the math will tell me what the actual answer is. Then we look at the other half of that, BC. So we have the pin at B and the external pin at C. External pin at C, it's becoming second nature now, a vertical and a horizontal reaction. Now what about B? Well, this is where Newton's third law comes in, the physics law that sounds like an action movie. For every action, there's an equal and opposite reaction. So if it's up and to the left here, it must be down and to the right here. And as long as I draw that, it'll turn out perfectly. Because remember, the math will tell us the direction. If the value at B turns out positive, then it was in the direction of both arrows. They're nicely opposite. If the value at B turns out negative, it just means, okay, it was in the opposite direction in both cases, and they still cancel out nicely.
I hope that was useful. There's plenty more videos in the playlist, but what's even more useful is lots of exam examples and exam specific advice. And that's what we do in the prep sessions. So join the Prep 101 Study Hub Facebook page to find out when those go on, and many of them are even free, so you definitely don't want to miss those. Hope to see you there.